Okay, now we have an ant weighing 0.016 grams moving across the picnic table at a speed of 2 meters per minute. What is the wavelength associated with this ant? So this is often done to show how absurd it is to think of macroscopic objects as having a wavelength. But know that this equation is correct. It's just that we can't see the wavelength of an ant, and that's what we want to prove. Though the ant, because it has a mass, because it is moving, definitely does have a wavelength associated with it. But let's find out, let's find out what its wavelength is. Now, joules are kilograms meters squared per second squared. So what I'm going to do is alter the joules into that form, and then this is times seconds. Just to show, now we see that we have the joules, J, that we were using is really kilograms meters squared per second squared. So you can see our mass has to be in kilograms. So we the mass here, which is 0.016 grams, is actually going to have to be in this form. If you don't, you're going to be off by a factor of 1,000. Got to use the right units. That's always have the right units here. Now, our speed is 2 meters per minute, but you can see there's no minutes in here, so it must be meters per second. So 2 meters per minute is can be converted to 0.0333 meters per second. So we just 2 meters per minute equals 0.0333 meters per second. So you just take 2 divided by 60. I'm just going to double check. Yeah, now we have everything the way we need it. Kilograms, meters, seconds, and then we have a second, the other second here that cancels, and we're just left with meters, and that's what we need for wavelength. So the wavelength of the ant is 1.24 times 10 to the minus 27 meters. The distance across the nucleus is about 10 to the minus 15 meters. So this is 1 trillion times smaller than the distance across the nucleus. So even though it is theoretically there, I mean it definitely should be there, there's also going to be wavelengths of everything else around it that would interfere with that, and would definitely be something that, even if that was the only wavelength that was in the universe, except for us, observing it, we still wouldn't be able to observe it. We have no way of measuring that, 10 to the minus 27 meters. So yes, macroscopic objects, using quantum mechanical equations on macroscopic objects doesn't really work out for us. Doesn't give us any useful information. Now, if we do use an electron, a subatomic particle that's moving at a really fast pace, let me use, instead of joules, I'm going to use kilograms meters squared per second squared times seconds over the mass of the electron. I happen to know it's 9.11 times 10 to the minus 31 kilograms. Should know that. It's a pretty common one, common to use that. And then 1.5 times 10 to the 6th meters per second. Now kilograms cancel, meters again, seconds here. We're left with meters, and we end up with 4.70 times 10 to the minus 10. And of course I did this earlier. But notice this is about, we're now on the order of angstroms, and this is about the size of an atom. So the wavelength of an electron moving around an atom is about the size of an atom. And that's not just by chance. That's electrons do act as waves, and they create standing waves, standing matter waves around the nucleus, and that's why the atoms are the size that they are. Now, what does the uncertainty principle tell us? Well, we have it here. States that we have the uncertainty in position and the uncertainty in momentum. And that there's always this uncertainty. We don't normally see it or think of it when we're dealing with, say, some baseball flying through the air or a car moving, we don't think of the uncertainty in position. But everything has an uncertainty in its position and uncertainty in momentum. And those two things multiplied together have to be greater than or equal to h over 4 pi. So there's always that inherent uncertainty we can't get around. And if we rewrite this equation, it tells us that the smaller the uncertainty in momentum, the larger the uncertainty is going to be in position. They play off of each other, and we could certainly exchange these. But if we try to really pin down the momentum of that particle down to almost zero, then this is almost zero, and then the uncertainty in the position blows up to the moon, and vice versa. So if you want to know one, either position or momentum, and then there's also one for energy and time, but we'll just stick with this. If you want to know exactly where an electron is, then by observing it, you've actually altered its momentum so drastically that even though you might know where the electron is exactly for that moment, you have scattered it around the room to a point where you don't know where it is the next second or the next moment. So trying to observe a subatomic particle is very tricky to do because you can't pin it down either by position or momentum. There's always some uncertainty. And then we have what is a wave function and how does it relate to an electron in a hydrogen atom. So we usually give it the Greek symbol psi, and this psi contains all information about an electron. That's all you can have. So the wave function contains all of the information about an electron. Generally, it is a complex function. That is, contains the square root of -1, or I, if you've seen that before. Well, it's hard to work with something that has an imaginary term. But if we square it, psi, that gives us a real value. The square root of -1 disappears, or gets taken care of by another square root of -1. And this is the probability of finding an electron in a region of space. So the psi just gives us all of the information about the electron, but in a form that's very tricky to work with because it has a complex term. If you square it, though, you end up with the probability of finding the electron in a region of space, and this is directly related to the orbital that we'll talk about, I think, next lecture.